Here we're asked to find the inertia about the x-axis, inertia about the y-axis, and inertia about the z-axis for the solid that's in the first octant and below the plane x plus 2y plus 3z equals 3. And the graph that they give is a similar graph to the one that we have. Since the equation for the plane is given with no coefficient on the x, I'm going to solve for the x and then adjust the coordinate systems accordingly. You could achieve the same results by solving for either the y or the z. Typically the z would be traditional. However, it's not going to be nice and easy like what we have here. So let's begin by starting our integral for the mass. As we just said, we will have our x's going from 0 to 3 minus 2y minus 3z. And then we will decide about the y's and the z's. And we will have our density function. To determine the limits of integration for y's and z's, we need to look at the projection of this figure onto the yz plane. So using a 0 for the x, we would have the equation 2y plus 3z equals 3. Now that's going to be a straight line where the y-intercept would be 3/2 or 1.5, and the z-intercept would be a 1. And so this is the region in the xy plane. As you can see, it is both z-simple and y-simple, so it doesn't really matter which order we do the y's and the z's in, as long as we get the appropriate limits on the integral. So I will just do a traditional vertical rectangle, which means dz. So I would want z going from 0 down here at the bottom to this value of z at the top. So I need to take the line, the equation for the line, and solve for the z. So then we would have 3z equals 3 minus 2y, or z equals 3 minus 2y over 3. Unfortunately, that doesn't come out too nice looking, but that's the way it is. So we'll use as our second variable of integration the z's, and they'll be going from 0 to 3 minus 2y over 3. And then finally, we have the y's. And as you can see on our picture, our y's are going from 0 to here. Now here happens to be the intercept on the y-axis for that line, which we already determined was 3/2. Of course, we're not actually asked to find the mass in this problem. However, you find the inertias by taking that integral and just inserting some factors. For example, the inertia about the x-axis would be that same integral with the factor y squared plus z squared. Now I will take out my TI-89 and perform that integral. That's going to be quite a bit of typing. So when I get this typed properly on my TI-89, you can see the decimal value comes out to be 0.006529, and to 3 decimal places that would be 0.007. Now, to find the inertia about the y-axis, we simply change the y squared plus z squared to an x squared plus z squared, which means that on my TI graphing calculator I can just change one letter and then press enter and have the whole new value. Finally, to find the inertia about the z-axis, we simply change the z to a y and enter that into our calculator.